For this lesson, we're going to work through quadratic applications. Now that we have some ideas of how to solve quadratic equations, how to find the maximum or minimum, we can use those for word problems. This first one shows the monthly profit of a small company that makes long sleeve t-shirts, and their profit depends on whatever price they set this shirt out to be. Here we have a graph of the function that's displayed in the equation f of x equals negative 50x squared plus 1700x minus 12,000. As we look at the variables, x is the price per shirt and f of x, the output, is the monthly profit based on that price. So in part A, we want to find the price that generates the maximum profit. We've been finding maximums, so we can find the vertex of this, but we care about what the actual price is. So that's the input in this particular one. The price that matches that input would be 17. So in this case, that's $17, which will generate a maximum profit. In part B, we're trying to estimate what we think that maximum profit is. So we're going to look at where that y value is for this particular point. It's a little bit above 2,400. It's not exactly halfway between 2,400 and 2,600, so maybe it's not 2,500 yet. So I might estimate it to be 2,450. If we wanted to, we could find the maximum because we have the actual equation. In part C, we want to know what price would the monthly profit be exactly 1,200. I'm going to find 1,200 and then look to see where does the graph or the function hit that value 1,200. And it happens twice. So it happens once when the input is 12. So this would mean at $12, the price would be exactly 1,200. And it hits again. So it hits over here at $22. For D, we're looking at when will the profit be at least 2,000. The at least means 2,000 or more, and we can see when it hits exactly 2,000. This hits exactly 2,000 at 14 and at 20. But because it says at least and not exactly, we have a whole range of values. Anything between $14 and $20 will produce an output or a profit that's at least $2,000. So we would say between $20 and, $14 and $20. And then E says, find the prices that would enable the company to break even. If we are breaking even, then we're not actually making profit, but we're also not losing any money. So the break even point would be when the profit is exactly 0. This happens when the price is set at 10 and at $24. So graphically, we can analyze that word problem, but we also want to be able to approach things algebraically. In number 2, we have a small rocket that's fired up into the air, and it gives us the equation that's going to model the height over time. So it says h is the height of the rocket in feet, and t is the time in seconds since liftoff. So in part A, if I'm finding the height of the rocket at time t equals 0, then I would plug in 0 for t. H of 0 would be negative 16 times 0 squared plus 48 times 0 plus 64. We end up finding that h of 0 is 64. And you can plug that in your calculator if you need to. That is also the y-intercept. So it could have asked you just to find the y-intercept, but we're now making that have some context to this word problem. In part B, so I'm going to write this out here for a second, not dollars, 64 feet. In part B, we want to find h of 2. So h of 2, we know how to plug a value in. The more important part of this question is interpreting that answer in context. So if I plug in 2, that means t is 2. And I'm going to use my calculator to figure this out. All right, so if I plug in negative 16 times 2 squared plus 48 times 2 plus 64, we get 96. So after 2 seconds, the rocket's height is 96 feet. In C, it says to write the model in transformation form. Now, another name for transformation form was vertex form. If I'm trying to convert something into vertex form, we first need the vertex. So I'm going to find that first. Let's get that vertex. We did this by finding negative b over 2a for your x coordinate. If I use negative b in this problem, negative b would be negative 48 over 2a, so 2 times negative 16. And you can use your calculator for that as well. Negative 48 divided by 2 times negative 16 gives you 1.5. Oftentimes we had been leaving that as an improper fraction. However, now we have context. So now that 1.5 is probably more meaningful than an improper fraction. So we're going to find the output when x is 1.5, or rather t is 1.5. So I should have really said t equals negative b over 2a. I'm still plugging this in, so 1.5 goes in for every t. And we can find the output. All right, we get 100. This means the vertex is at 1.5, 100. That's not what the question completely wanted. It wanted it in vertex form. So I'm going to rewrite the equation h of t in vertex form, which would be a x minus h squared plus k. That a value is the same a as from the standard form, and the vertex hk goes into the rest of it. In D, it says, how many seconds does it take for the rocket to hit the ground? So some things that we know based off of the context of this problem. There was an initial starting point at 64. This tells me the very first thing that we found, 0.64. And then the rocket's going to go up and eventually have to come back down. We want to know when it hits the ground right here. And that happens at a particular time. But the output at that has a height of 0. So we're setting this function equal to 0. This is another way of asking you to find the x-intercepts, but instead of just saying find the x-intercepts, it's asking it in context of hitting the ground. This function, if you can factor it, you can try factoring. You could also use the quadratic formula. One thing I'm going to do is factor out a GCF to make this a little bit easier. So negative 16 goes into all of those numbers. So dividing that 16 out, I get t squared If you need to do 48 divided by negative 16, it's negative 3. So minus 3t. And then 64 divided by negative 16 is negative 4. Now I knew that this one was going to factor, so I'm going to use the factoring method. But if I didn't know that it would factor, I could use the quadratic formula. T squared came from t times t, and we're looking for factors of 4. So negative 4 and 1 will work. On the inside, I get negative 4t. On the outside, we get positive 1t, which does combine to give me negative 3t. So this is factored form. When we had factored form, we would set each factor equal to 0. So then solving for t, I get positive 4 and negative 1. In context, that means 4 seconds and negative 1 seconds. There's no way that negative 1 seconds makes sense in context, so that's not going to be the solution. This quadratic function technically, would continue on in both directions, but this part doesn't really exist in the real domain because of what the context is. There's no way that the time was negative. So this value would have to be at 4. So this would hit the ground at 4 seconds. All right, so part E wants to talk about the maximum. It says, what is the maximum height the rocket attains, and how many seconds does it take for it to reach that maximum height? What's nice is that we have already found the vertex. If I had not already found it, I would need to do that now, but we did find it to be 1.5, 100. Both of those values mean something different in context. So the maximum height is our output, it's our y value. It reaches a maximum height of 100. The height is measured in feet, so that's 100 feet at 1.5 seconds. F is asking about when's the rocket increasing? When's that function increasing? Well, we've already described when a function is increasing before. A picture can be helpful. We did not have to draw a picture, but having some context helps. So we found the y-intercept already. We knew that the rocket was going up, and then it would eventually reach the maximum and then come back down. We also even know where that maximum is because we already found it. That's the vertex. So if I look for when this function is increasing, it's between 0 and 1.5. Remember when we were solving or describing when a function is increasing, we were using our x values. So this would be between 0 seconds and 1.5 seconds. And then find the domain and range for h of t. This function has a practical domain. It has a realistic domain because of the context of this problem. So the input is our time, and this is only going from 0 up to 4, because once it's hit the ground, the rocket's not going to do anything else. There's no need to keep going. So the domain of this would be 0 to 4. The range of the function, the outputs, the rocket's not going to go below the ground. Once it hits the ground, it hits the ground. But it's going to reach its maximum height of 100. So its y values, or the outputs, would be from 0 to 100. When you have a word problem, we will have to think about what's called the practical or realistic domain and range. We'll do one more that's similar to this. If you want to pause the video and go ahead and try it on your own, you can. In 3, we're standing at the top of a 300-foot tower. We toss the penny up, and then it's going to fall down. It's modeled by this function, So it's similar to what we just saw. A is asking for the height of the penny at t equals 0 seconds, just like what we did with the last one. So we're going to say p of 0. So negative 16 times 0 squared plus 8 times 0 plus 300. We get just 300. In context, that would mean that it reaches a height of 300 feet. Now, p of 1, if I plug in 1, I can still use my calculator. We've got negative 16 times 1 squared plus 8 times 1 plus 300. It gives me 292. This means at 1 second, or even after 1 second, the penny has a height of 292 feet. There's a few ways that you could state that same sentence. You could say something about like after 1 second, the penny is 292 feet above the ground, or some other format of that same wording. See, we're going to find the transformation form or vertex form, so we first need the vertex. The vertex in this one, same situation. We've got x equals negative b over 2a. I'm going to use t equals because our input is a t instead of x. But negative b over 2a would be negative 8 over 2 times negative 16. Putting that in our calculator, we've got negative 8 divided by 2 times negative 16, which is 0.25. And if I get the output, P of 0.25, we can plug that into our calculator. So negative 16 times 0.25 squared plus 8 times 0.25 plus 300 gives me 301. So the vertex was 0.25, comma 301. That's still not the actual question. The question is to write it in transformation form. So I'm going to rewrite that P of t function as negative 16 parentheses x minus 0.25 squared plus 301. We're using our vertex to convert it to vertex form. So how long is the penny in the air? Well, we can draw a sketch just like the last one. We found a y-intercept to be 300, and then it went up and came back down. It reached a maximum here at 0.25, 301, and then eventually it's going to hit the ground again, just like the other one. So this is asking for you to find the y-intercept. This would say 0 equals negative 16 t squared plus 8t plus 300. Now, I don't think this one's going to factor. So if it cannot factor, we're going to need to use the quadratic formula. Something that can be beneficial is still to get rid of that GCF, if there is one. What that does is it just makes all of your numbers a little bit smaller. And if I tried to find a GCF, I could look to see, does 8 go into 300, but it doesn't. 16 can't be the GCF, but 4 could be. So you could pull out a negative 4, and that would reduce so 4t squared minus 2t, and then I can figure out what's 300 divided by negative 4. Gives me negative 75. But I also don't have to pull out the GCF. I can deal with all of the bigger numbers. This is equivalent to if you had divided out that GCF by -4. That would be fine too. You're going to get an equation that's 0 equals 4t squared minus 2t minus 75. This equation, you can still try to factor if it does factor. And maybe it does, maybe it doesn't. All right, but I'm going to do the quadratic formula. Because I don't have a lot of space, I'm going to bring it down here to the right. So the quadratic formula said x equals, or t equals in this problem, negative b plus or minus the square root of b squared minus 4ac. All over 2a. Now this problem, I have reduced these numbers because I divided out that -4. So my a that I'm using is +4, b is -2, and c is -75. This would still work if you had used your original a, b, c. Your function or your values in the quadratic formula would just be larger, but eventually would need to be reduced down. So I get +2 plus or minus the square root of something divided by 8. And let's see what goes underneath that radical. So we have -2 squared minus 4 times 4 times -75. So it's a positive 1204. That value, if I put it into my calculator, does not even reduce down. It's something that maybe I could reduce by hand, but my calculator does not automatically simplify that radical. The issue is we honestly don't even care about what this exact value is because we have a word problem. So when we're thinking about this word problem, there are 2 times that it's going to hit the ground at this one and then this other negative value. So I just want to figure out where is this. So 2 plus the square root of 1204 divided by 8 is approximately, and we're going to use our calculator to figure that out, 2 plus the square root of 1204 divided by 8 gives me roughly 4.59. So I'm going to say 4.6 seconds. And then if we had done the -1, that's 2 minus the square root of 1204 divided by 8, we can get the other decimal approximation. It's roughly -4.1 seconds. That negative does not help in this problem. When we think about the time, it can't be negative. So I'm going to ignore that solution. The 4.6 seconds is the only one that has some meaning in this problem. So I would say this is in the air for 4.6 seconds. And E, it wants to know when the function or when the penny is at its highest point. That's the x coordinate, or the t in this problem, of the vertex. So it has a highest value of 301, but it happens when t is 0.25. So we're going to say at 0.25 seconds. And then F, what is the maximum height? That's your y value. It has a maximum height of 301 feet. For what interval of time is the height of the penny decreasing? We can see it's going down from the x value, the t value of 0.25, all the way to that x-intercept, which happened at 4.6. So I'm going to say between 0.25 seconds and 4.6 seconds. Lastly, find the domain and the range. Same situation, so the domain of this function is roughly 0 to 4.6. And then the range of that function is from 0 to 301. We're talking about the practical domain, the domain in context. The next video will go through a few more application questions.